Mixture densities. The mixture density is written as P of x equals to the summations of P of x conditioning on Gi times the probability of Gi, summing with index I starting from 1 to k, where Gi are the mixture components. They are also called group or clusters. The probability of x conditioning on Gi are the component densities, and the probability of Gi are the mixture proportions. The number of components k is a hyperparameter and should be specified beforehand. Given a sample and k, learning corresponds to estimating the component densities and proportions. When we assume that the component densities obey a parametric model, we need only estimate their parameters. If the component densities are multivariate Gaussian, we have the probability of x conditioning on Gi, which is approximately by the normal distribution of mu I and sigma I, and phi is equal to the set of the P of Gi mu I and sigma I, where I is starting from 1 to k, are the parameters that should be estimated from the IID sample. That is, x equals to the set x to the t for all index t. Parametric classification is a bona fide mixture model where groups Gi corresponds to classes Ci, component densities P of x conditioning on Gi corresponds to class densities P of x conditioning on Ci, and P of Gi corresponds to class priors P of Ci. That is, P of x is equal to the summations of P of x conditioning on Ci times P of Ci, where the summation is summing for index I starting from 1 to k. In this supervised case, we know how many groups there are, and learning the parameters is trivial because we are given the labels, namely which instance belongs to which class component. We remember from chapter 5 that when we are given the class x equals to the set x to the t, r to the t, where t is starting from 1 to n, where ri to the t is equal to 1 if x to the t is in Ci, and 0 otherwise. The parameters can be calculated using maximum likelihood. When each class is Gaussian distributed, we have a Gaussian mixture, and the parameters are estimated as the follows. P hat of Ci is equal to the summations of ri to the t summing for index t divided by n, and mi is equal to the summations of ri to the t times rx to the t summing for index t divided by the summations of ri to the t summing for index t. And Si is equal to the summations of ri to the t times x to the t minus mi times x to the t minus mi then to the transpose. So the multiplication of these three terms is summing for all index t divided by the summations of ri to the t summing for index t. The difference in this chapter is that the sample is x equals to the set x to the t for all index t. We have an unsupervised learning problem. We're given only x to the t and not the labels r to the t. That is, we do not know which x to the t comes from which component, so we should estimate both. First, we should estimate the labels ri to the t to the component that a given instance belongs to, and second, once we estimate the labels, we should estimate the parameters of the components given the set of instances belonging to them. We are first going to discuss a simple algorithm, k-means clustering, for this purpose, and later on show that it is a special case of the expectation maximization algorithm.